Okay, hello everyone. Welcome to our next lecture on linear regression. Uh, in this lecture, we'll introduce linear regression, what exactly it is, why we use it, and then we'll talk about a couple of metrics uh, that are used to typically understand simple linear regression. Uh, you know. Um, how good it is in terms of fitting the overall data. You might have actually in your one of your uh, math lectures, you might have come across equation of a line, right? Where you say y is equal to mx plus c, where m is your slope and c is some kind of constant, uh, which is typically the offset when your x is 0. So you'll typically see a linear line uh, with some slope and some initial offset. And a simple linear regression, right? Uh, almost, uh, is almost similar to, uh, uh, you know, uh, a straight line, right? Equation. The only thing is, in this particular case, uh, there are two things, right? One is this is one of the very common supervised predictive model where if you have right kind of you know features that can determine what the outcome should be, right? Then you can actually fit in a simple linear regression, and it can actually help predict the outcome for even the set of data point that it has not seen, right? So a very simple example, say could be uh, price of an house, right? You might have seen it in cities, right? So bigger the home, higher the price, right? So if you say that size of house is the only only thing that determines the price, we call size of the house as one of the independent variable, right? Because there is no control over it, and bigger the house, higher the price, right? So the independent variable is price of the house, and typically in your y is equal to mx plus c, your y here will be price of the house, your x will be size of your house, and then you try and fit in through all the data point and try and fit in a straight line, that kind of have the essence of overall data point variance, right? As you might have seen, if you take a simple scatter plot of all the house prices on one axis and size of the house on another, then uh, there wouldn't be any perfect line that can actually connect all the data points, right? So the idea here is actually you find the best fit that is having actually minimal deviation from all the data points at some aggregate level, right? And so yeah, we have actually sort of introduced simple linear regression, just to kind of again recollect the thought here. Basically, it is one of those statistical technique, right, that can model the relationship between a dependent variable and one independent variable. Right, so one independent variable is very very important because the moment you have more than one independent variable, which is typically the case with most of the real world example, then there is a variation of it that we call multiple linear regression that we'll see in the next video. So this will be, just for a very simple scenario where we talk about one independent variable, and that helps you get the outcome for the dependent variable that you have in mind. We have actually seen some, example around house prices and, say, size of the house, and So if you see here, the goal, in this particular case, as you saw, is finding a line that kind of minimizes the distance from all the other data point, right? So if you take size of the house, if you take price of the house, in many cases it will not be a very perfect linear relationship, the way you typically see in your y is equal to mx plus c, right? In your geometry class or wherever. Here, some of the housing prices will be having linear relationship. Some of them will be having some kind of offset, and so we have to actually find out a line that kind of minimize, right? Uh, all the data points that are not fitting on that line. We'll see some more detail about it. But for now, you might have seen that why you use regression is, if you have a large amount of data, you can train and try and fit in a model that can be robust enough, right? And you can use it to predict, the outcome for unseen data set. In case of housing, you can train it with all the available data set on one of the variable for simple linear regression. Of course, in real world life, and we see one practical example here, there will be lot many factors determining the outcome, and so it will properly fit for a multiple linear regression. But for simplicity, as long as you have size of the house and price of the house having some kind of linear relationship, this can be actually sort of extrapolated in that sense. After introducing primarily for your introductory data science class, right, exam, right, board exam, many a time it is asked that what is the formula that determine your simple linear regression, right? But this is very simple. You have to just remember y is equal to mx plus c, and the way you see y here is your dependent variable, basically the set of variable or the variable that you want to predict. Your x will be the independent variable, which is the variable that you use to predict your outcome, and m in some sense gives you some kind of multiplier that given certain unit change in x, how your price is going to change, right? And typically all the data points are not straight away simple y is equal to m. For example, now in this particular case, when say house, the size of the house is 0, maybe you can assume that price will also be 0. But there will be several other examples where even if your predictor variable is 0, there will be some offset, right? Because actually there is some random y, there is some starting point, right? Which is actually x might not be able to determine. So y is equal to mx plus c for simple linear regression, you have to always keep in mind. C is your intercept here, y is actually slope of the line from your simple linear regression point. And we'll now talk about, as you might have seen, right, the difference in simple linear regression from your geometry definition of a straight line is only one line couldn't fit all your data points, right? So if you see this as scatter plot, and if you assume that on y-axis you have price of the house, on x-axis if you have size of the house, then you can see there are a bunch of these data points, right? And your aim here is to find out a line where if you look at the difference from this line on x and y axis, and you kind of take the square sum of that, or deviation from this line, right? So there are several measures out there. The best fit line is the one that minimizes the differences, right? So basically you can have any random line out here. The best fit will be one where whatever metric you have in mind, that distance will be, overall distance will be minimum. There is a technique called least square method, given an introductory class here, introductory nature of the class here. I'll just kind of focus on you to keep this term in mind, right? And the idea here is there is a new term that we are calling it residuals, right? So if you look at this diagram, and if you assume that the straight line that you are seeing, and the red dots that you are having, right? So if you see the magnitude of these, or acquire some of these, right, whatever it is. So those are something that that typically what we call is has not been explained by this line, right? So there are deviations. So if you look at acquire some of these residuals, or actually absolute value of these residuals, right? The idea for least square method is to minimize the sum of squared residuals, right? So basically the vertical distance that we are talking about, square sum of these minimize across all your data point, right? If you want to define your residuals, what it will be for given data point xi. Say for example, when your size of your house is 1,000 square feet, right? And if 10 times in terms of say lakhs, right? If that determines actually the price of your house, then 1,000 square feet house becomes 1,000 into say 1 lakhs, right? So 1 lakhs into 10,000. But maybe the actual price could be a little more or little less than that, right? So if you take the predicted value based on this M and C, and if you take it from the actual, you have got the residual. And if you do actually square sum of it, right? So EI square and sum it across all the data point. So that's what that you have, sum of your square residuals. And the idea behind the set of techniques to get the best fit is to minimize it. So basically you sample your data points, you actually kind of hypothesize about actually a line that fits through all of these, and then basically from there on you start actually kind of moving this line in a way where more and more data points are aligned, and differences on either side is kind of minimized for the for certain threshold that you have in mind, right? Yeah, so let us take actually one example here, right? Now that typically when you are saying that y is equal to mx plus c, once you fit the baseline, you'll get some value of m and some value of c. Let's take a simple example, of say the length of your, study hours and the score that you might have got in some exam, right? Say that you have 2 hours 50 marks, 3 hours 60 marks, 5 hours 80 marks, 7 hours 90 marks, and say that you get that 10 times the number of hours is your score, right? So then you are actually having your regression line more like 10, and if you don't even study anything, you get 10 marks, right? So that's the initial offset that we are talking about, right? Even if you don't study, you might get some marks. So say 10 plus 10 into hours, right? Now how to interpret is, if someone studies 1 more hour, then he's going to get 10 plus 10 into so basically 10 more, right? So 1 hours 10 plus 10 into 1, that is 20. 2 hours 1 plus 10 into 2, that is 30, right? That way. So the way you interpret your m here is basically every incremental hour, right, is actually multiplied by that magnitude. Okay, so what we have talked so far, we just introduced what simple linear regression is. We made an assumption that there is a linear dependency relationship, right? So the meaning of linear is when you are changing your independent variable by some magnitude, right? It is not changing by say in a way where the relationship is not linear, right? So say for example, if it was changing a square or a square root or logarithmic of your independent variable, in that case the relationship wouldn't have been linear. So the basic assumption for simple linear regression is your outcome that you want to predict and the independent variable that you are having, they are linearly related in some way, right? And using that, we talked about that it is one of those techniques that helps you kind of model the relationship between your outcome and independent variable. We also talked about that we can use it to predict, your outcome or the predicted value that you have in mind once you actually kind of fit in. We talked about equation of this line, which is y is equal to mx plus c. M typically here is slope of the line, and this talks about how much unit change in your independent variable changes your dependent variable, right? And C, as we just saw in case of numbers of hours but marks got. So even if you don't test, you might get some marks. That's what C captures in this relationship. We talked about the baseline fit, and looking at the scatter plot and deviation from it for a given line, we saw that idea of least square is we are the vertical distance that you see here from the best fit line. The line which is actually the best fit line is the line where a squared sum of these vertical distances are minimal. We took some example and talked about how to interpret this data set, right? So now when you have done some fit, right, you can have model, as we say, right? Model is only as good as it has seen the kind of training data set, or as good as actually you have been able to kind of put your experiment in order. So many a time when you actually do some changes, or if you are having some variation in data point, your best fit might differ a lot, right? So the whole idea is then which one you call the best one, or which one you call your actually best fit. What is the quality of that best fit, right? So for simple linear regression, which is actually when you are just having one variable as your independent variable, there are two common terms. One is called mean absolute error, right? And as you saw here, eventually when you go through your training process, right, for a given independent variable xi, you will make a prediction based on your initial assumption, and then you are having access to the actual outcome there, right? So if you take the difference of that and take the absolute value of it, sum it over actually all the data point and divide by total number of data point that you are having. So this is not hat square. This is actually, let's call it just y1 hat, right? Yeah. How to interpret MAE? Lower is better, because you might how you'll get a lower MAE, right? If you look at this variable, the smaller these lines are, or the smaller the absolute differences are. If you are going to divide it by total number of data points, right, the smaller the difference, the smaller the MAE, and that actually reflect your better fit. So smaller is better, right, for MAEs. How to calculate MAEs? You saw it, right? So you'll actually take the predicted outcome and you take the actual one. You take the absolute value of that difference, sum it across all the data point, and divide by total numbers in your sample, right? We'll actually see one actual example just in next slide or so. Very similar to mean absolute error, right? So in many cases, mean absolute error could be a good metric. Root mean squared error is as we saw it is also used with mean squared error is the used for your best fit, least square best fit as well. The idea here is if you are having outliers in your data set, right? If you see the term, your absolute value is just focusing on the differences, right, from the predicted and the actual data point. But what root mean square is doing, it is actually going to square that out, right? So if you are having some outlier in your data set, it means that if you are having some data points which far away from what you have predicted and what actual values are, it gets actually magnified a lot, right? And so in that sense, RMSE is actually kind of gives you a robust fit when you are having a lot of outliers in your data set. If you remember, just for your reference, in some of our previous videos, we talked about outlier, using box plot, or Z score, right? So something say 3 standard deviation away from mean is actually a good candidate for outliers. Of course, depending on your analysis, and many other things, you can actually choose a different threshold. And many a time, the data set that you are having, some of the data points are actually far off from others. And if that is the scenario, then root mean square works better than MAE. Formula is pretty similar, mean square. So if you actually forget this, under root, right? The only difference that you are having here is that, rather than having an absolute value, you are squaring yi minus, yi hat. And then you are summing it up across all the data point as usual, dividing it by n, and which is the total number of, data points. And then you are taking a square root of it. And that's what I have root mean square error. Again, good thing with root mean square error is penalizing the larger error more than the smaller ones, because it's actually kind of squaring the residuals, and lower RMSE is better. Another important thing, if you see here, for the same data point, right, or for the same kind of better fit, in your absolute value, you are just going to take the difference, while in your mean squared error, you are going to square it out. So root mean square error will typically be having larger, numeric value, right? So this is important because some of your exam questions might be, around that. Yeah, so very simple interpretation, right? This is just talking about, bigger the error, bigger these, MAE and RMSE values are, and from your modeling perspective, you will prefer the one which is having lower numeric values. Again, RMSE is significantly higher than MAE, right? Given the nature, we also saw it, right? So we'll take actually one simple example, right? Say for a set of students, where they have got, some marks, and based on say a number of study hours, you have got a model to predict it, right? Y is equal to mx plus c kind of, and say you have got an actual and predicted, tabulated here. So if you want to compute MAE, what you have to do? You have to take the difference between actual and predicted, right? Take the absolute value of it and sum it. So 85 minus 85, 90 minus 92, 2, 75, 75, 80, 78, 2, right? So this 2, 5, 7, 2, 9, and 5, right? 14. That's why that you get it here and divide it by 5, right? So 14 divided by 5, you get 3.5. How to get root mean squared error? Again, you take the differences, square them. So 5 square, 2 square, again 5 square, 2 square. Sum them up, 58 divided by 4, 14.5. And then you take the square root of it, right? So 3.81. As you saw in the same example, your root mean square is 3.81, while your mean squared error is 3.5. So you've got the idea that root mean square is going to be for the same data point, and for similar fit, your root mean square will typically be higher than MAE. Okay. So here we talked about single variable linear regression, right? How to fit it, and how to assess the model performance using mean squared error and root mean square, mean absolute error and root mean squared error. We actually saw how to interpret MAE and RMSE, and yeah, so we also looked at housing price, on single one, or student marks for study hours versus whatever they get, right? And yeah, so we'll sort of stop. Yeah, so let's look at some of the common questions that you can expect, right? We'll actually look at some of the objective type questions, right? So say regression can be performed for which kind of variable, right? So if you see here, if you go and look at our definition of simple linear regression, what we are talking about, for simple linear regression, we are saying that this is a modeling technique that helps model the relationship between a dependent variable and one independent variable, right? And dependent variable here, in that sense, is not discrete, right? It's just like say fixed defined numbers, right? It couldn't be also actually say categorical, right? In that sense, so it needs to be continuous, right? So the difference here could be in one of our previous lecture we are talking about throwing a die, right? When you throw a die, you can get number between 1 to 6. That's a discrete. So if you want to predict, that you can't fit it through regression. But average score, in a given, set of die throws, right, that you can expect, that, if you sample, you'll get some actually, number between 1 and 6. And that will be kind of definition of continuous, where you can get any number between 1 and 6, right? So any number between 1 and 6 is different than one fixed number between 1 and 6, right? Because when you say one fixed number between 1 and 6, we call it categorical variable. That's typically modeled by another kind of technique that we call classifiers or classification. You'll see it later. So this is very important to keep in mind that simple linear regression, requires your predictor, the variable to be predicted to be continuous, right? Not discrete or categorical. Okay, which of the following statement is false? Regression can be done only for two variables. So see, we have just seen only simple linear regression, and here we are talking about one independent and one dependent variable. But there is a very simple extension of it. Right? The whole idea behind simple linear regression is to fit in a very simple line on one variable and kind of have some basic understanding about it. You very commonly use multiple linear regression, which we'll cover in next video, right? So yes, this is wrong because you can always have more than two variables, and practically that's a normal scenario with many or most of the practical regression modeling problems, right? Regression is a supervised learning technique. Yes, we might have actually covered this in one of our class, that your predictive models are having two broader categories: unsupervised, like k-means and all, PCAs, right? Those kind of things. PCA is principal component, right? Analysis. And regression, is something people look at both examples, right? In case of housing price, you have labeled data, right? This is the size of the house, this is the price. In case of student marks, right? Number of hours studied, marks achieved, and that's what when we are having level with you, we call it supervised learning. And regression is actually one of the most common technique in that, right? So yeah, B is definitely wrong. Regression can be done for categorical variables. So categorical variable again, right? Say male or female for binary, right? When you look at say fruits, apple, orange, guava, so if you fix number of kind of fruit, through the names we call it categorical, right? And those are typically classification problems. There is a variation of regression that we call logistic regression. Name logistic regression is actually kind of regression, but that is technically a classification tool, right? So yes, A is false. Regression can be done only for two variables. No, right? Which of the following are used for regression? So Canyon, K nearest neighbor. We'll actually see more of it in our classification video. Linear regression, yes, right? Not both of them, right? The value of RMSE is usually greater than the value of MAE. So look, this is why this question is very important, right? You saw it even in your, and I would like to kind of focus here, right? If you see here, your RMSE for the same data set is 3.81, right? And your MAE is for the same data set is 3.5, right? And why it is so? Because in case of mean square error, what you are doing is you are squaring the term, so you are amplifying it, right? And so it is always going to be higher than MAE. This could be one of the very good questions to keep in mind, and I have seen it is being tested regularly in your exams. So post MCQs, you'll be at least supposed to answer some short answers in say 100 plus words, right? So here actually you have to describe how you'll get the best fit, right? We talked about it, what a best fit is, right? And we talked about the technique for root mean square error, right? So basically what you do, you imagine a line, you take two random data points, right? And across that, so you sample 2 random data points, right? And across that you compute a root mean squared error, right? Across all the data points, right? And then you kind of again sample another line, right? Which is actually kind of, so more technical term is you sort of uh, sort your data points in some way, or you randomly choose it based on certain criteria in some way that you move from so basically, I mean, on purpose, I don't want to use more technical terms, which are actually kind of optimizers used for making this decision, because those could be too complex given your introductory nature. But the whole idea you can see here is you randomly choose 2 data points. If you make 2 data points, you can draw a line, right? And then you compute the mean squared error. You choose, then make another choice and compute the mean squared error. As long as then you decide a threshold, right? So the threshold could be say some very small number in mind. So as long as the difference between these two is changing, you keep rotating the line in some way, and then stop at some stage when you have actually looked through enough data points and your changes are not significant. Okay. What is the application of root mean square error? As you saw, right, root mean square is used for finding the best fit, right? And we just described some of these things. Write a short note on mean absolute error, right? So this is another technique to find out the quality of fit. You can take one example, so the steps describe why it is important. Another thing is, if you look at since this is looking at absolute value, so this is not as much dependent on the direction of changes, right? So that is again important. Okay, so far so good. We have actually covered large part of simple linear regression. We'll stop here. Do look at and do search actually more about these topics. You'll find tons of material. You just read through some of the topics primarily about assumptions on linear regression that we have not covered here, because some of those terms are not suitable for your intro level course. And then actually try and do find a best fit on some small 10-20 data points, right? Yeah, so we'll stop here and we'll see you again in the next lecture, which will be about multiple linear regression.